Hello, everyone. So welcome to this session. And my name is Florian Rössler. I'm the moderator for this session. I'm very excited to be here. With me today is Jacob Schreiber, who is a postdoctoral researcher at Stanford University, where he develops machine learning-based tools to tackle problems in genomics. He's also the developer of a cornucopia of open source tools in Python, including Pomegranate, which implements flexible probabilistic modeling, and Apricot, which implements submodular optimization for data subset selection. And previously, he was also a core developer for scikit-learn. And today he will be talking about Apricot, submodular optimization for minimizing redundancy in massive data sets. So I hope you all enjoy the talk, and over to you, Jacob.
Great. Thank you for the introduction. As Florian said, I'm Jacob Schreiber. I'm a postdoctoral researcher working on machine learning and computational biology at Stanford. Today, I'm going to be talking about this package, Apricot, that I wrote that aims to try to minimize the redundancy that exists in massive data sets. One of my motivations for creating this package is because data sets have been getting increasingly large over time. Back in the good old days of 1936, someone collected this data set that had 4 measurements of 150 different iris flowers. This was great because it was used as a toy data set for a long time because most statistical and machine learning methods could be run almost instantaneously on it. So you're able to develop and iterate very quickly. Then the computer vision community started to adopt this MNIST data set, which had tens of thousands of different images of handwritten digits, each with hundreds of different features, each feature being a pixel. So methods weren't quite as fast. Methods were still fairly fast on MNIST, but they weren't instantaneous like they were on Iris. Even later, the ImageNet dataset came out, which had over 10 million different images with over 50,000 pixels per image. So these were high resolution images, tons of examples, and you started to need specialized hardware in order to do computation. Even today, to train most modern methods, you need at least one GPU. You generally need clusters of GPUs in order to get this done in any reasonable amount of time. Progress didn't end there either. That data sets have been getting increasingly large. You now have data sets with billions of images. You have compendia of video or genomics data or health records. We are inundated with massive data sets now. And this is good, because the more data we have, the more we're able to train sophisticated machine learning models and evaluate them robustly to make sure that they work in a real world setting. However, as data sets increase in size, they generally also increase in redundancy. 2 researchers found that when they looked at C410 and C400, which are some toy data sets used in the computer vision community, that there were many examples that were very similar to each other. They were either slight rotations of the same idea or slight recolorations of the same image. Worse, there were some that were near duplicates. They weren't exactly perceptually the same, but they were basically slight recolorings of the same type, basically the same object at the same angle. Even worse than that, there were some exact duplicates in these data sets. When these types of redundant examples exist in training data, they can waste computational time because your model is exposed to them, but there's no new information in them for the model to gain. When they exist in across the train test split, there are some you can get overly optimistic estimates of performance. There's some philosophical things about how to construct a train test split that I'm not going to get into right now, but certainly within the context of training data, that having redundant examples can be incredibly wasteful. So we get to this idea of submodular optimization. Submodular optimization is to submodular set functions as convex optimization is to convex functions. Basically, a set function is a function that takes in a set of items and outputs a scalar. A set function is submodular if it obeys this diminishing returns property. And I swear there are only 2 slides with like math on them, and this is the first of those slides. The gist here is that a set function is submodular if it obeys this diminishing returns property, which basically says that some held out item V, the gain of adding that held out item V to a set X is greater than adding that item V to some set Y when X is a subset of Y. Basically, as X increases in size, the benefit of adding V decreases. So if that doesn't quite make sense, I have some examples that will hopefully clarify things in the next few slides. Something I really like about submodular optimization, though, is that you can be super creative in terms of the types of functions that you use. These functions don't need to be continuous or differentiable like they do in the convex setting. You can include things like if statements, for loops, all types of crazy things, as long as they obey this diminishing returns property. And a quick note on optimization, that optimizing a submodular set function, basically finding the optimal subset of items according to it, is NP hard. But this is really cool theoretical results showing that if you use the greedy algorithm, where you find one item at a time, you can get within a constant factor approximation of the optimal subset. This is an incredibly rare result. And in practice, you generally get almost the optimal subset anyway when you use the greedy algorithm. So I thought I'd just mention that. In the same way that people use convex optimization to optimize non-convex models, people use the greedy algorithm to optimize submodular set functions. So, that's a lot of theory and details. Now let's go into a, real world example that I'm sure you're going to encounter. Imagine you just finished watching the hit TV show Gossip Girl, and you were asked by a friend to summarize the show using only 2 of the characters. A plausible situation, I know. You might initially be inclined to choose Blair and Serena, because of course Blair is the best character and Serena is her bestie. But if you step back, you might think, okay, well, these 2 storylines are very intertwined with each other. So I don't necessarily want to choose both of these because we're going to be missing huge gaps of the Gossip Girl storyline. So you, having just attended a submodular optimization talk, realize that you can craft a submodular function that takes in a set of characters and returns the number of scenes that they appear in. Basically, what you do is you craft this function that goes through each scene and basically assigns a 1 if any of the characters in the set appear in it, otherwise 0. Now, this isn't exactly, it's an approximation of how important each character is to the storyline. But since the Gossip Girl storyline is so tight-knit and has no nonsense in it, it's a pretty good approximation. So imagine that you take the character Dan and you put it through this function. You might get something like they appear in 10 scenes in some particular episode. Then you go through and you put Blair in, and you see if they appear in 17 scenes, which makes sense because Blair is the best character. But you'll notice that if you put both Dan and Blair into this function, you only get 22 instead of 27. This is because they appear in some scenes together. Finally, if you then add Jenny to this function, you'll notice that the benefit is very marginal. And this is because Jenny's role in the show is either to act as a worse version of Dan or as a worse version of Blair. But this serves to demonstrate what the diminishing returns property is, that basically the more characters you add to your set, the less the benefit of adding Jenny would be. That either they are in that either some character you add is in scenes with Jenny that the other characters aren't in which case the benefit of adding Jenny goes down, or they're not, in which case the benefit stays the same, but the benefit would never go up. And so that's the key idea behind submodular functions. So now that we've identified a function that we could use and seen what the diminishing returns property is, how do we actually optimize this? I'm going to demonstrate this using just a general class of functions called the feature-based functions. The one we described is a feature-based function. This is a general class of submodular functions. Imagine that you have some data set where each row is an example and each column is a feature. What you would do, because this is a greedy algorithm, is you would start with the first example and you would try to measure the function value given it. Well, you take that. The first thing that you do in this function is you sum down the columns of all of the selected examples. Well, you haven't selected anything yet, and so the sum is just going to be the feature values for that first example. Then you apply phi, which is any type of concave function. Generally, I use square root because it's fast, but it's any function that has a diminishing returns aspect to it. So you apply that function, and then you sum along the resulting vector, and you get some value. And that is the value of, the set that you've put in. Now, let's say you scan through all the items in this data set, and you've determined that the first item is the best one, and you're trying to determine the second item to add, and you're considering this purple one. Well, now you do your sum as normal, which is going to be the sum of the purple feature values and the orange feature values. Note here that there are 2 purple feature values that have the same value. This feature here, where orange also has a high feature value, and this one here, where orange has a low feature value. When you apply your function with diminishing returns, what you'll notice is that the benefit of adding the purple example to this feature that already had a lot of it, a lot observed, is small, but the same feature value is much higher when you haven't observed the feature. This gives these functions a property where it's trying to choose examples where you are seeing features that you didn't see in previous examples. So this is good when your features represent different qualities of the data, and the higher value corresponds to having more of that quality. So this works for things like set functions, or when you have things like word counts, or if you have posterior probabilities or labels, or like a kernel matrix or something like that. It's not going to work well for things like XY coordinates. So here you might get some, additional value, and then you choose the example with the highest gain given the first feature that the first example that you already saw. Now, like all good talks, let's return to Gossip Girl. Imagine. So in this show, as you all know, there are these text message blasts that are set out by this character known as Gossip Girl, just in time to stir up trouble amongst all the main characters. The first one in the show reads like this: "Spotted, lonely boy. Can't believe the love of his life has returned. If only she knew who he was. But everyone knows Serena and everyone is talking. Wonder what Blair Waldorf thinks. Sure, they're BFFs, but we always thought Blair's boyfriend Nate had a thing for Serena." Perfect. It's exactly what my high school experience was like. It just brings me back to those times. So the idea here is that you might, if you have a friend that says, well, show me, I want to see how Gossip Girl talks about each one of the characters. So show me a set of blasts that talks about as many of the characters as possible. What you could do is you could go through all of the blasts, where each one of the blasts is a different row, and code them based on whether or not they mention a particular character in the show. And you might get something that looks like this, where the orange indicates that a character is mentioned in a blast and the gray means that they are not. If you take a submodular set function, which is just summing over the number of characters that you see, the first blast that you pull out might look something like this. Not so fast, you're not graduating until I give you my diplomas. Mine are labels and labels stick. Nate Archibald, something I'm not going to repeat. Dan Humphrey, the ultimate insider. Chuck Bass, coward. Blair Waldorf, weakling. And as for Serena van der Woerden, after today, you are officially irrelevant. Congratulations, everyone. You deserve it. Great. Perfect. Amazing. This is how I wish everyone talked all the time. But you'll notice here that the gist is that it has chosen a blast that mentions as many characters as possible because it's trying to optimize seeing as high feature values in as many of the features as possible. Correspondingly, the next one is poor Vanessa. Even Cinderella was given the courtesy of a stealth getaway. Then again, what's a trio of lovely stepsisters compared to Jenny Humphrey? Looks like it might turn into a unhappily after ever for everyone. You'll notice here that what's happening is that it's choosing a blast that mentioned characters that were not mentioned in the first blast. And so this is how these types of feature-based functions generally proceed, that they choose a first example that has a high feature values and as many features as possible, and then it iteratively choose subsequent examples that have high feature values and features that were not observed before. In contrast to feature-based functions, another broad class of submodular functions are the graph-based functions. These ones don't operate on examples that have featureization, but rather they take in a graph, like a network or like a social network or an interaction network, transit hub, something like that. Facility location is probably the most famous graph-based function and actually the most widely used submodular function that exists. It's literally used to locate facilities, thus the name. You can also think about it like a greedy version of the k-mean algorithm, or it's also known as the k-means plus initialization. The idea here is that you want to choose centroids that are very similar to examples that are not well represented by the already existing centroids. So to give you an example, I was sitting in an airport one day and I had the delightful gift of having my flight delayed by several hours. And as a tech worker with no understanding of how a domain works, I thought I was perfectly suited to solve this optimization problem. So I thought, why don't I just download a whole bunch of data from open flights and try to figure out where airlines should place their hubs in order to make my life more convenient. So here are all the airports that are located in the United States according to open flights. And when you connect them, you see a bunch of hubs starting to emerge. This is by no means all of the flights that occur in the United States. These are just the ones that were in the open flight database at the time that I downloaded them. if you take the airports that have the most number of flights total, the airports service a total number of 256 unique routes. And they include some of the airports you would expect, like Atlanta is definitely going to be a hub. Chicago is probably going to be a hub. Denver's a hub. These are classic hubs that almost every airline has. But if you represent this as a graph, where all of the nodes represent airports and all of the edges or connections between those airports, you can use facility location in order to choose airports that service more unique routes. And what you get is this. You'll notice that Bethel Airport in Alaska is chosen because it services a lot of airports in rural Alaska. However, the real reason that this is a more correct placement of hubs is because it includes Seattle, which is my hometown at the time. So because it included my home, that of course it had to be correct. But it also services 270 unique routes instead of 256. So you can imagine how someone will quite literally use facility location in order to try to locate where they place new facilities, because it doesn't involve, since you use a greedy algorithm to optimize it, it doesn't involve changing the location of any previous facilities, just choosing new facilities that are good for currently underrepresented places. But the main purpose of Apricot isn't just to implement submodular optimization. Generally, it's to work in the context of machine learning. So let's return to two toy datasets used in machine learning context a lot. The MNIST dataset that I talked about before, and Fashion MNIST, which is a similar type of thing, except it includes articles of clothing rather than numbers. If we run facility location, here, each of these data sets projected into UMAP space, and each of the dots is an example in the training set. If what we do is we run submodular optimization on these data sets, you'll notice that on MNIST, our facility location function pulls out basically each of the 10 digits except for 5. 5 is the worst digit anyway, so it doesn't really matter that it doesn't pull that one out. But this doesn't have any concept of labels. It doesn't know what a label is at all, what the labels are for these at all. Simply by trying to maximize the diversity of the chosen examples, minimize the redundancy, it ends up choosing examples that are, across the label space. And you can see it does something similar for articles of clothing, that it doesn't ignore these kind of islands that are far away from the other ones. It makes sure that it chooses all of them. And you can see that's fairly representative of the entire space. But the real test is what happens when you train machine learning models on it. If what we do is we choose only a subset of our data and train a logistic regression model on these tasks, how well does it perform? So you can see here on the x-axis what happens when we choose a certain number of examples. When we choose a certain number of examples using either random selection or when we use facility location. On the MNIST dataset, we see great results. That using only 200 examples, we see better results than when we use random selection with 2,000 examples. This is great. We can use 1/10 of the data and achieve even better results. Not only that, but in this case, we could probably even visualize all of that and just take a look manually at what our data looks like, basically using submodular optimization to create a summary that a human could interpret. On Fashion MNIST, it seems like we are consistently outperforming the median performance of using random selection, but that we're not seeing results that are as good as that are not as good as on the normal MNIST data set. And so that brings me to a point that it's super important to use the right featurization, to use the right submodular function with the type of data that you're using. In the same way that you wouldn't want to just use like a completely dense network on a high resolution image, you don't want to use the wrong type of submodular optimization on data. There's no function that works on all types of data. So you want to make sure that you choose a function that truly represents what's going on in the underlying type of data. Feature-based functions work well, like I said before, when each one of the features corresponds to some notion of quality of the data, and the higher value means having more of that quality. So you might need to transform your data a little bit in order to get it to work, but then these scale incredibly well. In contrast, graph-based functions require similarities between pairs of items. And so they are more general purpose, that they don't have any constraints on what the features need to mean that the similarities are calculated from, but they do require quadratic memory with respect, they need to store the entire graph in memory. So they require an amount of memory requires a number of edges. So how can we speed that up? Because if you have a giant data set and you want to run facility location, it's going to suck if you just can't do that because it doesn't fit in memory. Well, the first thing you can do is use sparse data formats. If your data is sparse, like you have a whole bunch of zeros and you want to run a feature-based function on it, or you have a sparse graph, you can just use that in Apricot. that you only need amount of memory proportional. You need only amount of memory and compute proportional to the number of non-zero entries in your data. And so if you're working with the sparse data, the bigger it is, the bigger the speed up that you can see here. On the left-hand side, we have the amount of time it takes working in a dense format versus sparse format for something with only 1% non-zeros. You can see that not only does, not only does the amount of time not increase as fast, but the speed up improves as you have more data. As you get a bigger and bigger data set, the benefit increases. A second thing you can do is use these algorithms developed for streaming submodular optimization. This is the setting where you only see each example once, and you need to know whether or not you want to keep it in your representative subset. It's a bit complicated, so I'm not going to go into the theory of how this works, but there's a gist that there's this parameter epsilon, which is inversely related to the coarseness. Basically, the smaller epsilon is, the more, normally proportional, where the smaller that epsilon is, the more fine-grained your distinction can be. Unfortunately, even in the finest grained settings, you don't perform as well as if you had all of your data in memory, but you perform significantly better than if you just take randomly chosen examples, which is the gray line on the bottom. So the benefit is that you only do one pass through your entire data set, and now you have your function. So what's in Apricot? We have a variety of built-in submodular functions as well as optimization algorithms. The goal is to be like PyTorch or TensorFlow, where even though we have some of these components built in, that you're able to plug and play them however you want. It's not like scikit-learn, where with linear regression, there's a few different optimizers built into it that you can only use, that you can use any optimizer on any function and vice versa. We have several speed optimizations that aren't talked about here, including several algorithmic tricks, a NumPy-based implementation that speeds up things a ton and provides multi-threaded parallelism, KNN approximations of dense similarity matrix, that even if you have a dense similarity matrix, you can still get a sparse approximation of it for faster speed, approximate greedy optimizers, and more. You can also write your own. It's really easy to write your own optimizer or to write your own submodular function and to optimize it. Like I said, these things can have all types of things like if statements, etc., all types of crazy stuff in them, and you can just plug and play them. We have a bunch of tutorials on the GitHub for how you can do this. Then finally, kind of an interesting point is that because all of these work on greedy algorithms, you can start off with a set of points that you want to build off of. If you say, I need to have this set of data when training my model, but I want to then choose points that are representative, that are minimally redundant with those sets, you can easily put that into Apricot and get a nice improvement there. So if you would like to see tutorials or documentation of the code in general, you should go to the GitHub page. If you want to see the paper behind some of the decisions we made when designing the package, you should read our JMLR paper on it. So thank you for your time.
Excellent. Thank you, Jacob. Spot on, really, here. I like it. Are there any questions? I think so far I haven't seen anything. Maybe have somebody now posting. But from my side, I guess a bit like naively asking, so what would be like how to phrase that? If I think about it in terms of data selection as a primary use case for something I could use just the next day, for example, that would be kind of the first thing that pops into my head. But what are maybe like some of the kind of second level use cases that I could think about?
Yeah, so the way I predominantly use submodular optimization is when is in the computational biology setting. The gist is that we don't have the gist is that in this setting, acquiring measurements is expensive. And so what we do is that we've performed a subset of measurements already. We train a machine learning model in order to make predictions for what everything should be. And then we run submodular optimization on the predictions in order to get a very diverse set of what we expect to be able to observe. And so having that first step of training a predictive model, and then the second step of subsequently choosing which elements to verify in order to get a very, non-redundant set of measurements given a limited budget, is really powerful in the computational biology setting. And really, it's going to be powerful in any setting where you have sensors and measurements are expensive. I know that Google does things like if they want to, and I've done this personally, where if you want to create a highlight reel of photos, that with this doesn't involve machine learning much at all, but I guess you extract feature representations using some sort of pre-trained model, and then you run submodular optimization in order to be able to filter out the, if you have 1,000 photos of your cat and a bunch of different photos of, your vacations, that you probably want a photo, one photo of your cat, but you don't want it to be 90% photos of your cat. You want to make sure that you're seeing that that's well represented and move on to other parts in your algorithm space.
Excellent. Well, thank you for that answer. I don't see any more questions, so I'm left with thanking you again for the amazing talk. I hope you enjoy the rest of the conference as well as all the attendees. And have a nice, for me, it's night, afternoon, or evening, wherever you are.
Thank you. Have a great day.